All right, everyone. So let's talk about error analysis. That's what we'll be doing in this video. So like I said, I'll be using the exponential smoothing and exponential smoothing adjusted trend. These are the two forecasts that we had with errors. Now let's say that our option was, does including trend make sense? Which of these two forecasts is better for me, right? So how do I decide which forecast is better? One forecast is better than the other. I look at the errors. Whichever forecast gives me a lower value of error is the forecast that I'm going to end up picking. Now, there are multiple values of error for both of these methods, but the idea is to come up with a single number representing error for each of these methods, so you can compare those single numbers against each other, and then you can figure out that, okay, if one number is smaller than the other, that's the better method because it has lower error, right? So what we're going to talk about are methods that aggregate all of these different error values into single numbers. So we are looking at error aggregates, right? So just smoothing with trend. Let me see. That's not what I wanted. Why is this? Okay. Okay. I had some issues with the recording software. All right. Proceeding. So let's do error aggregates. So I'm going to call this error aggregates. So I'm just gonna, in fact, I should have just copied the sheet over it. That's fine. Do this. We have everything in here. I just wanted to not miss anything. So what we'll do is I'm going to insert multiple rows because we have to do multiple error aggregates. Right? Okay. So we will, to find error aggregates, we will calculate the three error aggregates will calculate our mean absolute error, mean squared error, and mean absolute percentage error. These are the three error aggregates that we're going to calculate. So to calculate these things, we will need the absolute value of error first. So absolute value is just error without the sign, right? So that's the absolute value of error. All right, so absolute value of error. So you just say absolute. So the formula in Excel is ABS. So you just say absolute value of error. And it goes all the way down. So these are the absolute values of error. So I'm just going to again keep that to 2 decimal places. I don't need more than that. Now, once I have the absolute values of error, I can calculate a running total of the mean absolute error. So the mean absolute error, the mean absolute deviation. And the way we do this, so if you remember, I did this in class. So we are going to say that, okay, after period 1, what was the mean absolute error? After period 2, what was the mean absolute deviation? After period 3, what was the mean absolute deviation? So a running total of what the mean absolute deviation was as time progressed. And once you get to the very end, that the last number that you see, that will be your mean absolute deviation that you have right now. And to do that, we use the average formula. So let's say average starting from this number here. So we'll always start from the same number. So I'm going to make this a absolute reference. So I'm going to say, no. Nope. Can't work. Nope. Let's try this. Okay. Right. So I do dollar signs. So remember, dollar signs only for the first one. So you're saying you're always going to start here and you're going to end this running total wherever the current row is. So I'm going to end it right here for the time being. So you'll notice that there were dollar signs for the first part. There was no dollar signs for the second part, right? That's the average. I'm going to copy this all the way down. So what happens when I copy it down one level? So because I pegged the first, I put the beginning right here in time period 1, it is always going to begin in time period 1. It's time period 2 that's going to change. So when I go to time period 17, it's going to average all the way down to time period 17, right? So that's how the mean absolute deviation is going to get calculated. And that's my mean absolute deviation, the average of all of these different error values all the way down to the number. So by using the average formula, I don't have to worry about how many rows I have, right? So that will automatically get calculated. And that's the idea. So the mean absolute deviation right now is 7.16. What does that mean? It means that that's on an average, that's how much error I have. Now, if I am comparing this method versus the trend adjusted method, I will do the exact same thing, right? So I'm going to calculate absolute values of error. And I'm going to do MAD. It's the absolute value of error, right? And then, oh, let me, 2 decimal places, right? And then MAD is the average. So again, starting from the same number and ending at the same number. So the starting number has a $sign, ending number doesn't. For the first time period, there is only one error. So if you're averaging a single number, you get the same number, 6.75. But as you go down, notice that you have that right there. Now, so if I were to choose both of these methods, so when you're choosing between two methods, you have to pick a single error aggregate to make your decision. So let's say that I use MAD to make my decision. Then I say that the MAD for the first method is 7.16, while the MAD for the second method is 6.83. So on an average, the second method has lower errors. So I'm going to pick the second method. So going with exponential smoothing with a trend adjustment would be better when you're just comparing these two methods. Now, we haven't compared these methods with any of the other say the naive methods or moving averages or anything like that. You should be able to do all of that. For all of the methods, you should be able to calculate the MAD, right? So that's the MAD. That's one error aggregate. The second error aggregate is the squared errors. So I'm going to say error squared. So that'll be, you take the error, square the error, right? So again, I'm going to keep that to 2 decimal places. I don't want more than that. All right, and similarly, I can calculate the mean of the squared error. So MSE or the MESI or the mean squared error. So that will again be the average. It's a formula, average of this number here, starting at this point and ending at the same point, but the starting number has $sign. So you're making sure that it's always starting here. And there you go. So that's my mean squared error. So there you go. So my mean squared error right there, 60.87. Now do not compare the mean squared error with the mean absolute deviation, because first of all, this is a square and that is not a square, right? And also comparing them literally makes no sense. So this is the sum of individual absolute values, and this is the sum of squares, right? So that's the idea. All right. So similarly, I can do mean squared error for the second method of right here. Right? I can do error squared and the MSE, if I can spell things correctly. All right, so this will be the error squared. Go all the way down, and then the mean squared error, which is again average. So remember, the idea is you take the average, you start here. For all the averages, you always start at the same point, but the ending point is different based upon which row you are in, which time period you are in, right? So mean squared error going all the way down, and there you go. That's my mean squared error. So the mean squared error for the first method was 60.87. The mean squared error for the second error was 58.86. So if I was making a decision using mean squared error, then I would still pick the second method, right? Now, in this case, the mean absolute deviation and mean squared error sort of meshed with each other, but that will not always be the case. Sometimes the mean squared error, if the numbers are pretty close to each other, the errors are not that different, then in one case, the mean squared error might say, mean absolute deviation might say pick one method, while mean squared error might say pick a different method. That is always possible, but it is very rare. And in those cases, both methods are so close that either method might be okay. All right. Now, the final error aggregate that we'll talk about is the MAPE, the mean absolute percentage error. So instead of just looking at error by itself, we will look at error as a percentage of the actual demand value that you had. So it is the mean absolute percentage error. So you still need the absolute value. So we have the absolute values of error here. So I'm going to say absolute percentage. You know what? Let's write the absolute value formula also. So we'll say that this is, you take the absolute value of error, take the error, find the absolute value of error, and then you divide by the actual demand value. So you're essentially saying what percent of the actual demand was my error, right? So that's what you're saying. And again, you're getting rid of the sign because you're just looking at the magnitude of error and not the actual error itself. There you go. And this I'm going to represent as a percentage with 2 decimal places. So you're saying that in the first time period, your error was 10.78%, right? Absolute percentage. So similarly, I can calculate absolute percentage errors for all my different time periods. So some periods are pretty large errors, some periods are smaller errors, some periods are very tiny 3.45% error, for example. And using this, I can calculate the mean absolute percentage error. So MAPE. There'll be, again, average. So the same trick. We'll say average starting from here, always starting from there, but ending in different rows. So no dollar signs right there, right? All the way down, and there you go. So my average error is about 11.7%. That's for the first method. Now let's look at the final method. So we'll say absolute percentage here, and we'll do MAPE, Mad, Messy, and MAPE. All right. So absolute percentage is absolute value of error divided by the actual demand value, which is all the way up there, right? Okay. So again, I'm going to represent that as a percentage. 2 decimals. I'm going to copy this all the way down, right? So again, it's the absolute value of error divided by the actual demand value, right? So you're saying in the first period, you had an error of 6.75, which was 10% of the actual demand, right? So that's what you're saying. And then you have the MAPE, so which is the average, again, of the absolute percentage value. So it's going to start here, always start there, and end at the same point, but as the rows change, the ending points will change, right? There. That was my absolute percentage error. But if you look at the absolute percentage error, the absolute percentage error for the first method was 11.7%. For the second method is 11.44%. So again, it's the same. So this is better than that. So it is better to choose the forecast including trend with any of the 3 error aggregation methodologies, right? Okay. Right. So there's one last thing that I'll talk about. So this video has gone on longer, but there's one last thing that I want to talk about. We'll talk about that and we'll get going. Now, the last thing that I want to talk about with errors is the idea of, well, let's say that I did this error analysis and I say, hey, okay, fine. I chose forecast including trend. That's my forecasting method and I'm keep going. Now, after a certain point, let's say that you see that errors are starting to pile up and you're not forecasting well. How do you make sure that on an ongoing basis, your forecast is remaining good, right? So to do that, you calculate something called a tracking signal. A tracking signal is a number that tells you how good your current forecasting method is working, right? So I have my forecast values, I have my error values here. So what I'm going to do is I am going to keep the MAD because we're going to need the MAD if I remember correctly. Is it the MAD that I will need? Yes, I'll need the MAD. Okay. All right. So keep the MAD. So we're going to calculate. Let me hide these numbers. Okay. Let's calculate something called the average error. Now this is a running error. So running error is just a sum of all the error up to this point without changing the sign, right? So that's the important piece here. So the value of running error is just the sum of all the error starting from this number here. So it's always going to start here. So I'm just going to do the same thing. It's going to end in the same point, right? But as you keep going, the sum will change. So you're adding the errors. Now, notice that in the second one, the error becomes negative but it's smaller because you're directly adding the error, including the sum. just keeping a running tally of what your error is. So it's a running tally of error. Then we can calculate the tracking signal. The tracking signal is, if I remember correctly, it's MAD divided by the running total of error. Right? Right. Again, I'm going to keep this to 2 decimal places. Right. So it's the MAD divided by the running total of error. No, actually it's the other way around. I'm sorry, I messed up. So this should be the running error divided by the MAD. Yes, right. Sorry, it's a running error divided by the MAD. That's your tracking signal. I'm gonna copy this down. Yeah, so it's the running error divided by the MAD. So the running error is also sometimes called the bias. So I'm just gonna call this the bias. You know what? I put running error in parentheses. It's called the bias. Okay. Right. So again, tracking signal is the bias or the running error divided by the MAD. So I think I copied this down. Yeah. Okay, I did. So now, what does this do? So this keeps track of how much error you are accumulating and how it compares to the MAD, and it also gives us a good sort of benchmark of how well our forecast is doing. So when you set up a tracking signal, you set up ends or the edges for a tracking signal. So the edges could be depending upon how frequently or how accurate you want your forecast to be. The edges can be anywhere from a +3 to -3. So that could be your good range. Or it could be +4 to -4, +5 to -5, even +6 to -6, but definitely not more than that. So this is related to 3 standard deviations and 6 standard deviations away from the mean in normal distribution. Very similar ideas. It's based off of the same thing. We are going to assume that it follows a normal distribution and all of that. So with all of that in the background, what we are saying here is that if this number, so if let's say that we set our boundaries to be +3 to -3, if at any point in time your tracking signal goes past 3 or -3. So in this case, it became less than -3, again became less than -3, again here became less than -3, right? Then it came back into being okay. So you can say that, okay, 1 or 2 times if it goes outside this range, I will be okay. But if it goes outside the range, let's say 4 or 5 times, then I'm going to reevaluate my method. In that case, what it means is that your current forecasting method is not working well. You will need a new forecasting method. In this case, it went out twice, it came back into the range, it went out again, but then it's corrected itself and it's keep going, which means that there were a few points where you were not forecasting well, but otherwise the forecast was okay. So in this case, now the decision becomes subjective. There are some cases where even a single number going outside the range will mean that it will trigger a reevaluation of the whole forecast, depending upon what your company wants to do. But or you might say, okay, I'll wait for 3 or 4 times is okay, but once it goes past 4, I'm going to stop, or goes past 5 or 6, I'm going to stop, right? And the ranges itself doesn't have to be +3 to -3, it could be +4 to -4. In each case, if it's +4 to -4, there's only once when it went slightly below -4, otherwise the rest of the time the forecasting method was doing okay. All right. So that's the tracking signal. It tells you whether the current forecasting method that you've picked is working well or not. Right. Okay. So I'm going to stop this video here. In the next video, what I'll do is we haven't talked about seasonality. What to do when you have seasonality in the data. The next video is going to be it's going to be a slightly longish video because I'm going to go over the whole method of how to handle seasonality and all of that. So it's going to take a little bit. But all the information will be in that video. All right. I'll see you all in the next video. Take care.